Go.
Excellent. Thank you very much. Well, good afternoon and good evening, everyone. Welcome to the January 23rd HamSCIence Zoom Telecon. It's good to see all of you. We've got I guess we call it a quorum. We've got a screen full and then some, depending on the size of your screen, I suppose, but a good group here today. Good to see everyone. Today we're going to have an interesting speaker. I see Diego Sanchez is ready to go in a few minutes. Diego got his undergraduate degree at New Jersey Institute of Technology, working with Mary Lou and Gareth and some of you others that are on this call today, and then moved over to the University of Scranton. Was that last summer, Diego? I think it was.
Yep, it was last summer.
Yep. So now he's doing his research, working on his master's degree in computer science at the University of Scranton. And Diego's done quite a few presentations and posters for HamSCI over the years at various workshops, and been on the road a few times, recently to CDAR last fall and AGU near closer to winter. So he was going to graciously agree to give us his presentation that he gave at AGU back in December. So without further ado, Diego, why don't you share screen and we'll see what we see.
Yep.
And if everyone can mute, that'd probably be a good idea.
There we go. Sorry, if Zoom will let me actually click on. There. Can everyone see my screen? Awesome.
That's great.
I just want to make one slide. So the talk I'm giving today, it is the same work that I presented at AGU. Though AGU I gave a poster. This talk was for the ERSI the NRSM meeting. So the International Union of Radio Science, the US National Radio Science meeting that was in Boulder a couple weeks ago. And so I presented my work on climatology of large-scale traveling ionospheric disturbances observed with, sorry, 1 sec. Can't see my screen entirely. 14 megahertz amateur radio using a novel automated detection technique. And for this meeting, it's a little unorthodox, but I did dedicate a bit of this talk to explaining to the audience what HamSCI is and what we do. Now, this conference was radio science focused, so there was actually a lot of interest in HamSCI, especially a lot of the discussions after the talk. And I tried to do my best to answer any questions and try to get hype up HamSCI. I think I was mostly successful. There are quite a few people who are actually interested in the HamSCI workshop, so I'm hoping maybe I managed to increase interest, and maybe we'll have a few new people this year come to the workshop. But yeah, so I really focused on this part, and especially on the data that we use for this study, which are reverse beacon network, WSPRNet, and PSKReporter. Again, I dedicated quite a bit of time just really trying to show the quality of the data that we have here, that we've been using, that the ham radio community has been producing. And just to highlight that, I was showing that just the increase in the amount of data that these passive receiver networks have been accumulating over the years, and it just keeps going up and up. And not only that, but the consistency of the data throughout each year. So on the right-hand plot here, for the U.S. average total spots of 2017, there's not a significant difference from month to month. So any seasonal patterns that we observe that I'll show that we've been finding in our data would not come from any of these other reasons. So the main phenomena that we're attempting to observe with the ham radio data, so these are called traveling ionospheric disturbances. These are quasi-periodic variations in the F region electron density. They typically have wavelengths of greater than 1,000 kilometers, periods from between 30 to 180 minutes. And there's a whole bunch of different other instruments that can observe them. However, for the most part, there's really low geographical coverage of these existing instruments. And not only that, but one of the big ones, the super darn radars, they don't even have full year-round observation capabilities, which is something that we actually don't have with the ham radio data. We have year-round observation capabilities. And so these traveling ionospheric disturbances, as they're going through the ionosphere and perturbing the ionosphere, what we find is that it comes up in the data as a type of HF fading. So as the ionosphere becomes perturbed, we see these changes in the actual distance. So the refraction changes and the distance that we observe communications happening is changing as the wave goes through. And so the technique that we've been using, this was actually published, Nathaniel published this 2 years ago in 2022, I believe, in February. And just to kind of show real quick how we observe these TIDs. So on this top plot here is the actual ham radio data from RBN, WSPRNet, and PSKReporter. So what we do is, we have the distance from transmitter and receivers for each datum, each spot. And on these 2D, we create these 2D histograms here, where our y-axis is the actual distance from transmitter and receiver throughout the day in UT time. And so usually what you'd find is if it's a quiet day, there's no disturbance whatsoever, you should see this kind of flat structure. So as on 14 megahertz, there's no nighttime observation capabilities. But as the sun comes up, that's when refraction 14 megahertz becomes possible again. So you would see where you have this decrease in the minimum skip distance throughout the day. But we keep finding these wave structures in the data, which are TID structures. And so whenever we have these really nice quasi-periodic wave structures, these are indicative of a TID structure in the ionosphere. And so for this paper, we made a comparison for the 3rd of November, 2017, comparing it to SuperDarn here in the middle plot and GNSS TEC plots. And, this particular TID structure, we found, you can observe it with the other instruments as well. And so here's just another example. So these are our more current heat maps that we've been generating. So this is the amateur radio, WSPRNet, PSKReporter, and RBN observations. This one up here for the 15th of December, 2018. You can see a very clear, very strong LSTID structure. And I really wanted to just emphasize what the difference between a day with an LSTID and a day without one, so a quiet day, which would be this one down here for February 25th, 2020. And you could see how, there's no wave structure. There's just this minimum skip distance that goes down, peaks at around noon, and then goes away again for 14 megahertz. And also, for this technique, we've been really focusing on just the continental United States. So you can see here on the right-hand side, this map showing these are the midpoints of each spot data that we have. Another thing, so just to further validate the technique, Nathaniel had performed a bunch of ray trace modeling using the FarLab software, or PyLab, sorry, the PyLab software. And so for this one up here, we have on the left-hand side, this is real GNSS TC data for December 15th, 2018, where you could clearly see these very pronounced wavefronts from an LSTID. And so on the right-hand side, using PyLab, you generated, it was a propagating sinusoidal LSTID with a wavelength of 1,000 kilometers. Source, believe was, 78 north, 75 west, with a period of about 120 minutes. And, very similar structure from the actual GNSS data. And so from there, once we have that perturbed ionosphere using the IRI model, we simulated a grid of transmitter and receiver paths. So any paths that were less than 3,000 kilometers. So this is something that I forgot to mention. We really try to focus, trying to hone down single hop communications. We make the assumption that wherever the midpoint of our communication is, that is where refraction is happening off of the ionosphere. So maximizing those single hop communications for that assumption. And therefore, so we try to limit any communications that are, we focus on those communications less than 3,000 kilometers. So for this ray trace simulation, only paths that were less than 3,000 kilometers. And so every 10 minutes between 12 and 24 UTC, randomly selected 3,000 transmitter receiver paths were chosen and plotted. And, we see very similar wave structures to the actual real data when we have LSTID structures for that particular day. And so one key thing, previous studies that we've been doing have been all manually searching for these LSTID structures, which can be very, very time consuming. Oh, did someone say something? Sorry.
Oh no, I'm sorry, I sneezed. I thought I was muted.
Keep going. I don't know if that was someone was trying to interject. So previously we've really only been doing this manually. So manually generating daily plots of the ham radio data and manually searching them visually for these LSTID structures. And I'm sure a bunch of you are familiar with Bill Engelke's work from the University of Alabama. So they've been trying to come up with a machine learning approach to automatically detecting these LSTID structures. But one key thing from a lot of the work that they had done was they actually did quite a bit of pre-processing that allowed to grab this bottom side structure from the data. And so using all their pre-processing technique, there's a bunch of rescaling, smoothing, thresholding, column-wise percentiles, and those are what's used to identify that bottom edge of the first hop skip distance. And so from there, we use a first sinusoidal fit. So we're trying to get rid of the natural pattern that naturally occurs in this data as the 14 megahertz, naturally that bottom edge that appears to detrend the raw data. And so, we get that first sign fit, we detrend the data. We also make a selection. So using 15-minute rolling coefficient of variation, we're trying to select a period with, what's the word? I guess the smoothest structure that we can observe. So this particular day is a very nice day. But there are a lot of days that have a lot of noise, or there's really only maybe a section of the plot that's usable. So we try to filter for that. We try to select the longest, most contiguous section of data that we have by using this coefficient of variation. And so from there, then we find that first sign fit, we detrend the data, and just to show what the detrend we're trying to do, we're trying to eliminate on this bottom right plot here, this natural curve that is present in the data for every single day. We're trying to eliminate that. And so from there, we apply a bandpass filter. So we're only looking at LSTIDs They typically have those periods of between 1 to 5 hours. So applying a bandpass filter just to get rid of all those other all that other noise that we have in the data. And once we have that filtered data, then we apply a second sign fit. And this is actually where we grab all the disturbance parameters from. So the three big ones that we're looking for is the amplitude of the disturbance, the period of the disturbance, and then we re-add that detrended edge from earlier to find the minimum skip distance. So the absolute lowest value that we have for that specific day. And then from there, this is where I started looking at those sign fits that we were generating using this automated detection technique and performed a climatology for those three parameters. So for disturbance amplitude, minimum skip distance, and period. And initial results, they show very clear seasonal patterns. So we see enhanced amplitudes during the winter months. During the summer months, for the most part, amplitudes go down, which indicate less LSTID activity, with some enhancements throughout the years. But for the most part, we observe much more and much stronger LSTID structures during the winter months. Another interesting thing was when looking at that minimum skip distance. So we do see that the minimum skip distance, as we expect, it is larger during the winter months. It drops during the summer months, but it appears to actually keep getting overall higher throughout 2017, 2018, 2019, 2020, which does coincide with the solar cycle, which does have a minimum here in 2020, and then eventually it starts to go back down again overall. And then much less clear looking at the period, it was much noisier, but we do see that there during the summer months, you tend to have these lower periods during the summer months, which does coincide very nicely with that minimum skip distance data that we're observing earlier. So conclusions, the LSTIDs were mostly observed during the winter months with a decline during the spring and fall and occasional enhancements during the summer. The overall increase in the minimum skip distance from 2015 to 2022, where after 2020, it does come back down again. The automated detection method is consistent each year when observing seasonal patterns. Big thing, the available spot data from RBM, WSPRNet, and PSKReporter, especially PSKReporter, has been growing significantly over the years. An issue, though, that we do have currently is that the edge detecting algorithm, it was pretty much optimized for 2017 to 2019. The amount of data available before those years and after those years has been causing some issues with the algorithm. Anything before 2015, there's just not enough data to really make any observations. And anything after 2020, we have to go back and tweak the algorithm to really optimize for those years to take into account all that extra data that we have available. And so further development of the automated technique is required to help with the curve fitting accuracy. And that's all. Thank you. Any questions?
Hey, Diego,
Yes.
thank you very much. It sounds like most of the results from the data that you had were in line with, I guess, for want of a better term, your expectations. It sounded like things were going the way you expected, but were there any results that you found or saw that were different than you expected? Or just leave it at that were different than you expected?
Not really. This was we were expecting to find more LSTID structures during the winter months as opposed to the summer months. A big thing, however, was we were previously looking at this manually, and a key thing was the way we categorized that data was so we basically split each day into hour chunks. So if we did make an LST observation, the basically just jotted down that there was an LSTID for that hour chunk. And we kept observing that there was a spike in LSTID activity, typically around June, for the years that we were making these manual observations for. And I think just because of the resolution, we have much better resolution for looking at the amplitude up here. We were finding that we do see these spikes in the summertime, but they're not necessarily all focused around that same time. That was something I was not expecting when looking at these results.
Thank you very much.
Diego, I have a question. Bob Jonk here. How are you doing?
Very good, thank you. How about yourself?
Yeah, all right, glad to meet you. I saw on your Vita there, University of Colorado, so I like that. Really interesting paper. I mean, a lot of data there, and it's amazing what you're able to pull out of the Whisper database. It's impressive. I was going to ask, why did you select 20 meters? Why not 30 meters or other frequencies? What would you expect to find if you went to a different band, or what would the issues be?
So there are a bunch of other bands that we have been looking at. 1.8, 3 megahertz, 7, 14, 21, and 28 megahertz. So the big issue first, the majority of the data that we have from RBM, WSPRNet, and PSKReporter is 7 and 14 megahertz.
Mhm.
They're just considerably more data for those two bands. And the issue though is that 7 megahertz, even though there's quite a bit of data there, it's really hard to pick out daytime structures. It has some decent nighttime observation capabilities, but 14 megahertz was just we were able to make the best, clearest observations using 14 megahertz during the daytime. For the most part, it's really hard to make any observations on any of the other bands, but the data is there. I'm curious if that might actually get better in the future using newer years, whereas there's so much more data available. But as of currently, 14 megahertz is the focus, just because it's the one we're able to make the most and best observations with.
No, that makes sense. Well, thank you very much. Nice
no
talk.
problem. Thank you.
Yeah, I have a question.
Yes.
You said that there are waves passing by a location at about a spacing of about 1,000 kilometers.
Yes.
So I thought of the stupidest question that I could think of was why that's about 300 hertz. And have you ever thought of listening at approximately that frequency to see if there's anything going on?
I have not actually. I don't know if this is something maybe Nathaniel. Have you ever thought of?
I can't. Have I thought of listening at 300 hertz? You mean 300 hertz in an audio passband, or 300 hertz on? Can you repeat the question again, Ed?
Well, the question is, these things are passing by a single point on Earth,
Right.
at a spacing of about 1,000 kilometers, and if you consider that to be a wavelength and convert it to a frequency, that would be probably around 300 hertz. And so I was just, I'm saying, well, is there anything going on at 300 hertz?
Yeah, but it's not an electromagnetic wave per se. It's a electron density wave.
Good point, but good point.
So I'm not sure. The way I think you would hear it is if you had a CW transmitter somewhere you'd hear the amplitude increase and decrease with a periodicity of about, 1 to 3 hours. So I don't think you would be able to detect it the way you're just trying to describe.
This is just a theoretical question in order to because
Yeah.
is there something going on at this frequency?
Yes. I think we should see oscillations with similar periodicities in the grape data, the CW grape data.
Yeah, there's something about, my mind's been maybe similar to yours, Ed, or a little bit differently about, I guess they call it almost sonification. As a ham radio operator, I'm on the air, I hear QRM or QSB, excuse me. I hear the fading going up and down, and we think these LSTIDs or MSTIDs may be contributing to that as the ionosphere is moving up and down and the point of refraction keeps changing. So I know we've had some talks and things about sonification of data for different projects over the years, and something in my mind just tells me I'd like to hear what this sounds like. Then you can speed it up, probably, and maybe not slow it down. But who knows what might come of that.
Diego?
Yes.
Great. Very nice presentation. Thank you. Very, very thought-provoking.
Thank you.
If I may refer to a couple of your slides, you showed one slide with a nice visualization of the wave fronts through TEC.
Yes. So
And I would anticipate, given the link to the auroral electrojet, that those are north to south propagating waves.
yes.
Right, so keep that in mind while we look at your distribution map of, you showed the midpoints of the paths. Yep.
This one right here.
And so those paths would have any mix of east, west, north, south, northeast, southwest angles. So have you selected by angle of incidence to the TEC wavefront to look at any possible variations in the skip distance?
So, but you mean to pick out directionality of the waves, or?
Well, I naively, I might expect that with a north-south propagating LSTID, that if you were to look at a small angle of north-south radio propagation paths, you're looking at normal, at right angles to the wavefront.
Oh, okay. I see.
Whereas if you're looking very obliquely, there may be some paths that are actually along a wavefront, and I would expect to see perhaps different behavior.
So this is something that we have been doing already. The big issue with this, however, is which is why a lot of the studies that we have done so far look at the entirety of the continental United States. The second you start making smaller sections, the amount of available spot data in those smaller sections tends to just not be enough to make any kind of observations.
Okay.
In the 2022 paper, however, Nathaniel did exactly this, and you do see he made smaller sections, and a particular very active day, you can see that it behaves differently. So when making horizontal slices as opposed to vertical ones, which I think show, that there is directionality, the directionality of that wave for that day. But for the most part, it just gets very difficult. The amount of spot data available in those smaller slices is so much lower. Something that I'm really excited to really try in the future is using these newer years. There's just so much more PSKReporter specifically, so much more available data. And I'm curious if making these smaller sections for newer years will actually we'll actually be able to continue to make these types of observations. And then also allow us to pick out even smaller structures. So it just currently the technique isn't able to pick out anything smaller than an LSTID. But I think that what you're mentioning would be a way to get even smaller structures.
So
Okay.
Gwen,
Thanks-
what you
thanks, Phil.
asking is or proposing is analyzing east-west propagation paths separately from north-south paths and seeing if there's a difference of the skip distance?
I believe that's what he was asking. Yes.
Hey, Gwen, I
Correct.
put the link in the chat to the paper. If you look at figure 3, you
Yeah.
can see the slices that I did. And I've
Oh.
done that manually for a single day.
Right. Okay, thank you. Opening that up has really slowed down my link, but I'm really glad that you're looking at that, and I very much take on your point that in reducing the number of observations, it makes it difficult. But yeah, that's good.
Ultimately, of course, and when you're very interested in this part of it, is that it'd be very nice to be able to see what the actual wave angle is at the receiving stations, both altitude and azimuth. Because that may not be, doing this center point analysis is probably not accurate.
No, but I think that's the one of the key issue. Well, I don't issue, but just the nature of the technique. To be able to make these observations, we just have to have has to be big enough to be moving the majority of the ionosphere over a large enough area.
Well, yeah, but the point I'm trying to make is that there's nothing that says that it's actually effectively reflecting off the center point. It could be anywhere to the side or
Correct. Yeah, and I
could
think
even be backscatter for all we know.
yeah.
But
That's
it is, yeah, that's the best that we can do without further information. I'll also point out that, just to close the loop, we're looking at these in the Doppler measurements at HF with the GRAPE data. And we also are seeing these same things in Doppler data from the AM broadcast band.
Oh, Gary, you're muted.
Sorry about that. On the slide you're showing now, in the lower left-hand corner, we've got that arc, and I believe you said that's kind of a typical day without an LSTID.
Correct. Yeah, that
Okay,
is
so
a
that's
quiet day.
sunrise on the left and sunset on the right.
Yep.
If you were to look at that same graph at different points during the year, would that curve change? Because like in the northern hemisphere, the amount of sunlight that hits the earth changes throughout the year.
So that curve will drop during the summer.
It'll drop. Okay.
It'll get lower during the summer. And that is, we do observe that for the most part in this plot. Yeah. So the middle plot here, that absolute lowest shortest distance communication for each day, that's what this middle plot here shows. And you do see here during the summer, it gets significantly lower as opposed to the winter months.
Mm.
Yeah, every single summer it goes down. It's lower.
Is there a difference? I'm thinking when we talk about winter and summer, they're obviously flipped between the northern and southern hemispheres. Would it be possible to look at generate a graph like that for the southern hemisphere? Do we see the mirror image of that, or am I thinking about things wrong?
No, that's something we could definitely do, as long as we have to find an area in the southern hemisphere that has significant amount of data to be able to
Sure.
do a similar study.
Yeah.
I'm actually not, I haven't really looked at, so the 2 or 3 big areas I've really looked at so far has been continental United States, Europe, as well as the Atlantic a little bit. Those areas just have such a huge concentration of spot data. Europe considerably more than even the US. But Southern Hemisphere, there are some hotspots. And I think some there are studies that are starting to look at those. But I personally haven't done that yet.
I wonder if there's enough ham activity in Australia to get enough data.
Or the African continent would be a real challenge too. So, but
Yeah, African I suspect is lower activity, but Australia might have fairly good activity.
Yeah, I don't have handy right now, but I don't know, Nathaniel, do you have a full world spot data map available?
I sort of do. Come back to me in 2 minutes.
Okay, sorry, I don't want to put you on the spot.
I don't know. I do have one from a couple years ago. Just come back to me in 2 minutes.
Okay.
Okay, so I'd like to say something. I think Ron had a good question, what was unexpected? And so in this particular slide we're looking at now is something that I find unexpected and have not been able to find a good mechanism for yet. So if you look at the center panel, the one that is the skip distance, and it goes up and down and up and down, and those are the seasons. And we have colored orange backgrounds. Whoa. Orange backgrounds to the ones that are particularly high. So the orange is the winter time. All right. And so we see 1, 2, 3, 4, 5 really good winters, and then a kind of witchy winter toward the end there. And it does go up. But then if you look between each of those in the sort of greenish areas, there are the places where it goes down. And that's the summertime when the sun is giving us a lot of radiation to ionize the ionosphere deeper down toward the Earth's surface. But the thing that's interesting to me is that they are not symmetric. The summer is short and the winter is long. And that keeps on going. And I don't see why they shouldn't be more even. So what it turns out is that the drop, when you go from the skip distance being high to low, so that goes from winter to summer. And then when you go from, it goes back up from summer to winter. Those are very particular days, and they're fairly consistent throughout this whole run of years. And they are not when you'd expect it to be. They're not the equinoxes. They're both of those dates are moved summerward from the equinox. I don't understand why that could be, but we're working on that. If anybody has any ideas, let me know.
Yeah.
I have the world plot now.
Okay.
So, so this is the RBN and WSPRNet data combined from 2009 through 2020. So about 11 years worth of data, and it's broken up by bands, 1.8, 3.5, 7, 14, 21, 28 megahertz. And so you can see we tend to be very Northern Hemisphere centric. There is more data than this because this doesn't include any of the FT8 PSKReporter data, which would be quite a bit more. But I'd imagine, my guess is the distribution is going to be somewhat similar. This particular technique works very well when you do have very high concentrations of midpoint spots. So it works well over the US. We've looked at Europe a little bit as well. I know Diego hasn't shown that, and we haven't really published it, but the plots that we have generated over Europe, they look good also. And then this, we have not looked over the Atlantic Ocean, but it looks like it's a high enough density that might be interesting to look at. We might be able to get some information from the southern hemisphere here with this technique, but this is on a log scale, and this is significantly more sparse data than up here.
I do notice there seems to be a hot spot between Australia and New Zealand, coincidentally.
Yeah, look at that right there.
I think another thing to keep in mind, so where you're filtering in this one for much higher distances, right? It's not 3,000.
This one, yes, this one goes out to 10,000 kilometers here. These plots.
Yeah, I think I'll especially the Australia hotspot down there might a bunch of we might lose a lot of spot data when we filter to try and get that single hop propagation distances.
Right.
Is that
But Australia to New Zealand may not be too bad.
Yeah, I was going to ask, is that spot that's between Australia and New Zealand an indicator of communication between the two locations?
I think that's reasonable, yes.
To know they're talking to each other.
I mean, that hotspot we see in the Atlantic Ocean is most definitely US to Europe communications.
Yeah, I wonder where communications from here to Australia, say, would show up on this map. I know the primary propagation from here in New Hampshire is to the west from here.
We really need to encourage a lot more people in Australia to become hams and New Zealand.
Oh, there's also South Africa. There's a reasonable amount, because I have a number of books by South African hams.
It might also be interesting, as we do hope to deploy whisper receivers down in Antarctica, and we know that the other stations have it. Other countries have those down in Antarctica as well, to think about how we might look for these types of TID signatures in the observations they make, even though it's not a high density set of observations the way we're showing it here. Signatures may still be in that data.
So there are plenty more opportunities. That's what I guess that's what we're saying.
Yes.
That's what I was trying to communicate at this conference I was at.
It's 4:50 now. I want to thank Diego first of all.
Thank you.
And Diego is working very hard at pushing this project ahead. He is meeting with Mary Lou and I, multiple times a week, and also with Dr. Mark Fenner. He's going to start meeting with Dr. Fenner to talk about how he can turn his work into a Masters of Software Engineering project. So got quite a bit going there. I know, Gary, I had asked Kukai if she would be able to come on this meeting too, and I see her sitting quietly in the wings. So I'd feel remiss if I invited her and didn't give her a chance to give us a quick update on how things are with her. I know she has been to this, what we call the space meeting, over the past little bit as well. So.
Wonderful. Sure. Let's hear from Kukai. Absolutely.
Okay, so now as a space project of NASA, so we try to register HamSCIence metadata to the NASA space system. And now we are focusing on the HamSCIence spot data and personal space weather data. So yeah, we try to categorize and we still need to do many things, and I need to contact many people in our community regarding this from now. Okay, so yeah, please collaborate kindly. Thank you.
We'll have to talk more about this. And Kukai, I think we should set up a meeting in the next week or so with you, Bill Engelke, and me, especially to talk about iSWAT.
Of course, let's do it.
Thank you. Back. Anything else on the agenda, Gary?
Well, just a couple of things. I know I saw a couple of things in the chat about the workshop. I know the local organizing committee will be meeting tomorrow, and we're hoping to get the hotel information out pretty soon. It's not quite ready yet, but we're getting pretty close. So,
it's up on the
anything
site
else?
now, actually. I put it up on the site a few days ago,
Oh, okay.
but we haven't email blasted it out.
Yeah, I just saw that. So I picked up on it because my question was at the top and then my answer was a bit down.
Okay, great. Any other comments or questions on the workshop before, we got a minute? No. Nathaniel, is there anything else you wanted to cover in particular?
I think that's it for the main session. If we have a minute or two after, I might do some discussion with after the recordings shut off.
Sure. The other thing we got to start thinking about Dayton as well too. I'm not sure when I know last year we approached Yasmin about not Yasmin, about the table and that sort of stuff too. So that's probably shouldn't let that go too much.
That has started.
Okay.
Dayton very kindly sent me an invoice this morning and said, if you want your table and your reservation, please pay this invoice. I did forward that to Ward this morning and asked him if Yasmin might be interested in paying for it again. So we have started that discussion. I'm working with Salisa to try to get hotels for the University of Scranton people, squared away. So we're working on that also.
Excellent. Okay, good. A lot of eggs in the basket to roll around.
There really are.
There sure are. One other thing I like to do real quickly before we end, I've been catching up on some of my reading the last couple of months, spending a lot of time looking at QEX. And there's been a couple of course, Gwen's had an article in there recently. I think it was, last year. And there's been a couple of others that I might want to approach the authors to speak at here on Thursday afternoon. So let me share my screen real quick. Let's go to my desktop. I'm not sure. I don't know if Nathaniel, Gareth, or anybody else in the call recognizes either of these names. But this was an article from QE.
Yeah, I know Daniel Emmons. He's in the service, I should say. He's in the Air Force. So I know him.
Okay. As I know we were talking about sporadic a little bit last year, there's some interesting things in this paper, one of which is their use of CW or Morse code beacons as a data set, which is something we've not really run across too often in the past.
Yeah,
but there's some interesting things here.
Daniel's in Dayton.
Yeah, right path it looks like.
Yep.
Although I think the last I heard, I think he's deployed now. So that's the last I heard. He wouldn't be, because I'm on a Eclipse related project with him, and I think he was saying he was deployed, and so he would essentially not be doing research for a bit. So
okay, well perhaps I'll approach Ken then, see what he's got to say. You never know. So
good idea.
Okay, that's it.
Yeah, I think it's the newest QEX that has a couple of things on propagation. One having to do with long delay echoes.
There was also an interesting article earlier in the year on repurposing an old navigation beacon as a VLF station, and I think I may check in with the author on that too. I've got to finish reading it more thoroughly and taking some notes, but it's a possibility too. All right, that's good for me. Is there any other questions or comments? Diego, again, thank you very much. Not only was it a good presentation, but it brought forth a lot of questions too, and that's always a good sign that people are digging into what you're talking about. That's what I like to see.
Thank you so much.
Mhm. If there's nothing else, we'll end the recording and call it a wrap for the week. And hope everybody has a good week, and we'll see you next Thursday, most likely.
7-3.